Hi everybody, this is Project 2, video 2 of 2. The first video for this project is linked below, along with the Kickstarter link for the multi-sensor electronic learning board. Got about 10 days left, so if you're interested, have a look, rather. Before we get into this laser tripwire circuit or light sensor circuit, we're going to need to go over our resistor divider theory. So this is our standard resistor divider, and we use that to create specific voltages right in between. We're going to call the voltage in the middle of the divider VDiv, for V division, the voltage at the dividing point right here. So what we have here is a VCC. VCC is just a power supply reference. We've got, so it's 5 volts in this case. We've got RA and RB. Now in the case of RB, which we'll see in just a few minutes, RB is actually our light dependent resistor, our LDR, and that changes based on how much light is hitting it. So the calculation to determine what's at VDiv is VDiv equals VCC, so 5 volts, divided by our total, so RA plus RB. And then once we have that calculation, we multiply that by RB. So if we have an RA of 10K, an RB of 10K, what's our VDiv going to be? So we break the calculation out like this. 5 volts divided by RA plus RB, 20K, so 5 volts divided by 20,000. Once we have that, we multiply that sum by 10K, which is our RB. So why don't you stop the video for a second, try to calculate it out, and see what we have at our divisor. 2.5 volts should have been your answer. If RA equals RB, it's always half of your VCC. So if we had a VCC of 10 volts, RA was 10K, RB was 10K, our VDiv would be 5 volts, because 5 volts is dropped along RA, 5 volts is dropped along RB. That's in the case of 10 volts being our VCC. In any case, when the light dependent resistor, let's say that's RB, is receiving a lot of light, say we've got a laser pointed at it, or you're in a very bright room, it'll have a lower resistance in the range of 5 to 10 k ohms. When there's darkness surrounding the light dependent resistor, the resistance goes way up past 100 kiloohms. So we're going to do 2 examples. We're going to do an RB of 10K, where we would see 2.5 volts or potentially even less, but we're also going to talk about when there's darkness hitting the light dependent resistor. So let's change this value to 100K. So why don't you stop it again and recalculate what our V division is. You should have received an answer of 4.54545454 repeating volts. So if you round up, 4.55 volts. So it could be more or less depending on how dark the environment is. In the case of light, if it's really there's a lot of light hitting the sensor, it could be about 1 kiloohms. So we're just trying to get a basic understanding of how we're going to be using our voltage divider for our secondary laser tripwire circuit / light sensor circuit. So let's look at the actual schematic. We've got 5 blocks here. Our light sensor circuit, our variable resistor, which we will tune to a certain voltage as a reference for our comparator. Our LED will be acting as an indicator, and the option we have for our buzzer or relay attachment. We may or may not use this. We won't use it in the video, but we will talk about it. Anyhow, yesterday we used the AC coupled side of the light sensor circuit for another laser tripwire. In this case, we're going to be using the div1 side, and this is the equivalent of VDiv, because there's a voltage divider here. We've got a fixed 10 k ohm resistor and a light dependent resistor, and the resistance varies depending on how much light or darkness is hitting it. So let's just assume that we're going to see 2 volts on this line roughly 2 volts when there's a lot or less, 2 volts or less when there's a lot of light hitting the light dependent resistor. And then we're going to see more than 4 volts when it's complete darkness. So what we're going to want to do is find a voltage right in between for a reference. So we're going to tune our variable resistor to 3 volts. And we're going to connect that to the comparator in just a second. Now, you can easily measure the voltage on VDiv by connecting your multimeter negative lead to the ground line on the power supply pin block and your positive probe, red probe, to the div1 line on the main pin block. And what you can do with that is you can essentially look around to see how the resistance changes based on how much light is hitting the sensor. And we will actually do that in just a minute. But let's just, for this case of argument, 4 volts here roughly when there's a lot of darkness, 2 volts when there's a lot of light. So we're going to have a 3 volt reference connected to either the positive or negative input of the comparator. Depending on our output logic, the logic that we wanted the output, we can simply switch these up to invert it. But first of all, let's put 3 volts from the VAR pin, the variable resistor pin on the main pin block, to the positive input. So and we'll connect the div1 line to the negative input. So we've always got 3 volts on the positive input. If you go back, if you don't remember our talks about comparators, go back to the project videos. They're also linked below. Remember, if there's more voltage on the positive than there is on the negative, the output is VCC, high, 5 volts. In the case where there's more voltage on the negative input than there is on the positive input, the output is low, 0 volts. So, as we said, in darkness there will be roughly 4 volts here. So if we've got 4 volts in darkness on our negative input and 3 volts on our positive input, the output is going to be low because there's more voltage on the negative than there is in the positive. In light, let's say there's 2 volts on it, 2 volts or less. 2 volts to the negative, 3 volts to the positive, the output will be high. So, basically you can turn on the light, turn the lights off while you're powering it, and the output will be low. Turn the lights on, and the output will be high. So, to test this, we're going to connect the CP1A, the comparator 1 output, to the LED pin. Now again, if we want to switch the normal logic on the output, all we have to do is switch those 2 wires, and we basically invert logic. From there, once we've tuned it the way we want to tune it, all we have to do, if we want to drive our buzzer or relay attachment, is connect to the input line. Both of them have a VCC line, a ground line, which we connect to the main pin, the power supply pin block, and then we've got an input, sometimes labeled I/O, and we can drive those because it's got its own driver circuitry on it. Anyhow, I hope I wasn't too confusing here. I know that when I talk about inverting logic, blah blah blah, it can get a little bit confusing, but if you have been watching the videos, this kind of should be second nature to you by now. So let's try hooking this up on the learning board. As always, you want to make sure you're selecting the right sensor. Use a 2-pin jumper to jump the LDR pins on the sensor selection pin block, and next we're going to want to plug it in. Things to remember: our VAR variable resistor is right here. Turn the voltage up by turning the little spring clip clockwise. To turn the voltage down, turn it counterclockwise. And the VAR pin on the main pin block is on the lower left, second from the bottom, labeled VAR. Our div1 pin from the light dependent resistor circuit is right here, lower right, third from the bottom, labeled div1. So to tune, first of all, just for fun, let's take our multimeter, and you can actually stick it on the 7805, the negative probe. You can stick it on the 7805, the back of the regulator, because that's connected to ground, or you can connect it to the ground on the main pin block right here. On the power supply pin block. So sorry, I know it's a bit clumsy here. I'm trying to make sure that you can see what I'm doing. So to tune the VAR pin, we want to tune that to 3 volts. Right now it's sitting at 2.5 volts. all I have to do is turn the VAR variable resistor right a few times, and I'll get that to close to 3 volts. And we did that in video 1. We tuned that variable resistor, so if you need to look back, please feel free. Now, in normal lighting, here's the LDR right there. If I look on the div 1 pin, what do I see? 0.92 volts. So there's a fair bit of light hitting the sensor right now. If I put my hand over it, it's not even really all that dark. It goes up to 2.9 volts. So I was off a little bit, but as soon as I turn off the light and there's no light hitting that, it's going to shoot up to more than 4 volts. So in any case, we're going to follow the plan. We're going to tune our variable resistor to output to 3 volts, and then we're going to make our connections. So stop the video, tune your VAR pin to 3 volts, and then we'll make the connections to our comparator. So step number 1, we're going to take our div 1 pin from the light sensor circuit, and we're going to connect that to the C1- pin on the comparator pin block on the bottom. So div 1 to C1-. Now we'll connect our VAR pin that we've set to 3 volts to the C1+ pin. Sorry if my hand's getting in the way. Lastly, we're going to take our CP1A, our comparator output, on the main pin block, and connect to our LED pin. As we can see, the output is normally high. So what I'm going to do is I'm going to turn this around so you can see the LED better. I'm going to start turning the lights on and off. So you can easily fine-tune this based on your environment by testing the voltage on the LDR on the div 1 pin, and using the comparator and the variable resistor set as a voltage reference to make this really sensitive. Now also what we can do, the output is normally high right now. Remember me talking about inverting the logic? All we have to do is change the inputs to the comparator. So right now we've got the div 1 line from the LDR circuit to the negative input of the comparator, and the 3 volt calibrated voltage from our variable resistor to the positive input of the comparator. What if I switch those two? I made the switch, and now the output is normally low. So I'm going to turn up the lights a few more times. Oh, the LED's on. So why don't we plug in our laser attachment and point it at the LDR, and then we can make a laser tripwire. So I've connected the laser to the power supply pin block, red to 5 volts, black to ground, and I'm pointing the laser at the light-dependent resistor. Now our circuit isn't very sensitive right now, but I'm going to go turn off the lights, and I'm going to come right back and I'm going to break that laser beam. Breaking the laser beam now. Notice the LED? So as long as I'm breaking that laser beam in the darkness, the LED turns on. So the output going to the LED, the output of the comparator, is normally low, which is what we want for our relay or buzzer attachments. So let's connect our buzzer attachment. I've switched the comparator wires again so that the output is normally high. The LED would be on right now with the laser connected, with the laser or light hitting the sensor. As soon as we bring darkness into the equation, it won't work right now because there's too much light in the room, but as soon as the output is brought low, the buzzer unit, which we've connected again to the CP1A output of the comparator, will emit an alarm. So this is another laser tripwire. As long as the laser is breached in darkness, the output of the buzzer will sound. So let me just turn off the lights. I'll come right back, and I'll break the laser beam. So there you go. Now I'm going to show you the connections on the board so that you can actually have a better idea of where everything's being connected right now, and I'll do that right now. all that I've done here is connected the div1 line to the A0 pin on my Arduino and connected ground from the power supply pin block to ground on the Arduino. I've powered both boards, and I've used the analog read serial code. That's it's a basic code that's included with your Arduino under examples. Basic analog read serial, and you open that up, you load your Arduino board, and you open the serial monitor, and you can actually see a number that's been taken from the ADC, and it prints it on the screen continuously. So let's have a look at those numbers. Sorry if you can't see that too well. I believe it's a 10-bit analog to digital converter that the Arduino has on A0. I might be incorrect. So this is just normal lighting. We see a value of about 243 roughly. And those will change a little bit based on line noise and whatnot. If I just cover the sensor with my hand to offer a little bit of darkness, it goes up to 400. If I take my laser attachment, plug it in, and shine it at the light sensor, it goes down to as low as 13. So if I unplug that attachment and I just put both my hands over the LDR, it goes up to as high as 860 something. So you can basically program your Arduino to be really sensitive based on certain lighting conditions. So if, for instance, if light sensor equals 100, ignore. If light sensor equals 200 or more, activate something. So that's just an example. I'm more of a PIC person myself, but I do tinker with Arduino occasionally. Anyhow, thanks for watching, guys. I know that I kind of stumbled through parts of this, but I hope you were able to get what you needed out of this video. Next, we're going to talk about the vibration sensor in Project 3.